Hello, guys. Can you hear me? Hello, everyone.
Yeah, hello. Yes, sir, we can hear you.
Hello, sir.
Yeah.
Sir, live started, sir.
All right. Thank you so much.
Thank you, sir.
Okay. Half an hour more. Okay. Okay. So it's nice to meet all of you. And then it took some time for us to have these live sessions. Because I was tied up with many other things. I hope that you're enjoying the course. Feel free to reach out to us if there are any questions. Some of you might feel that it is way above your thresholds, but believe me, I think if you spend some time on it, you will find it useful. This course, essentially, I'm very fond of this course because whatever I think I have understood from this area in the last 10, 12 years, we have tried to consolidate all of that into this course. And at least to my knowledge, there is no equivalent course. I mean, there are a couple of courses from, for example, Vlad Shalive and others. But this one has some kind of additional features that I think are interesting for anybody working on nanoscale photonics and things like that, quantum photonics and so on. Okay, so it's my pleasure to offer this course. I would like to make it as interactive as possible. So please speak up and ask any questions you have. It can be very, very basic. It doesn't really matter. Okay, we're happy to take any kind of questions. If you have any other feedback, you think that something is not explained well, you can reach out. Yeah. All right. So let me just try to look up who is here. I think, hello, Kumaran. Can you just briefly tell us where are you from, or any questions if you have?
Good evening, sir.
Yeah, good evening.
Sir, myself Jagan actually. So it's my brother's lab. Actually, my name is Jagan. So it's my brother's lab. So that's why I'm showing Kumaran. So
Okay.
myself Jagan Bhatis. So I'm a scholar, a research scholar, doing PhD in evolution of technology.
Okay.
And I feel that the course is up to my expectation, and I get to know many things with especially the transfer matrix. I'm looking for that method. I can find exact materials or something. So I got to know many things in this courses. So till now I have no doubts. So if you have any doubts, I will post my comments.
All right. Yeah. Thanks. Thank you so much.
Thanks.
So let's move on. Lakshmi, do you have any questions? Can you introduce yourself?
Hello.
Hello. Yeah.
Sir, I'm Lakshmi from SRM University.
I'm sorry?
From SRM University, PhD scholar, sir.
Oh, okay. SRM University. Nice. Okay. Yeah.
Okay.
Do you have any questions?
It's not questions, just I need some practice problems, sir, because I have that much of physics background.
Okay.
That's why I'm asking multi-layer stacks, calculating the fragment. I'm getting confused.
You're getting confused in the multi-layer stack?
Yes, sir.
Okay. So if you have that issue, right, what I would suggest is go to my webpage, rather not my webpage, go to GitHub, look for NQP public, Naresh Imani. You will find a GitHub repository for this. Where is it? Sorry. You'll find a GitHub repository somewhere. Can somebody find it and post it on the group link, please? I think I'm not able to find it right now here. It should be available.
Yes, sir, I have shared.
Okay, good. So Lakshmi, I think Nandana has shared one link now. Okay, I'll require to log into this.
I was just thinking about genetic.
So you'll find this link. This is what I think Nandana has shared right now. Okay, you'll find this if you go into the T matrix. You'll have a lot of examples. For example, T matrix of a 1D photonic crystal or just a multi-layer stack, right? You'll find these examples, which will actually help you solve all of this, and then it's actually validated against literature. So these are a good starting point for you to check and try these things. But you can actually modify the code a little bit with Python, and then you'll be able to manage. If you have any questions, you just can send us the code, and we can take a look. All right.
Okay. Remaining.
Unfortunately, it's very difficult for us to because it's numerical code, right? If you have 10-15 layers, I can't analytically solve it. But I'll take this as an example, and maybe we'll think about something. Okay. Next time I'll try to put in some examples. We'll try. Okay. Anything else?
Nothing. Everything is fine.
Okay. Swapna Sagar, any questions? Swapna Sagar or Ayushi, any questions? Please introduce yourself and anything, any comments, questions, concerns. We're okay to take them. Ayushi, Goswami? No? Swapna Sagar Sahu? All right. The remaining folks are, I think.
Hello, sir.
Yeah, hello, Swapna Sagar.
Hello, sir. Yes, sir. Sir, I am a PhD scholar from BIT Vellore. Sir, can you please explain how the detuning is like? What is the significance of this detuning? How it works? Like, I have a doubt in that things.
Which tuning are you referring to?
To tune the laser. Suppose you are getting some tuning the laser. So what do you mean by the detuning, and why this kind that frequency we need?
No,
how it is related to?
I think you're talking about the laser cavity interactions. Is it right?
Yes, sir. Yes, sir.
Okay, I don't know. Let me recall the week number. Week number 9 or 10?
Yes, sir.
No, not even 9.
No. It is
week 8.
Yes, sir. Week 8.
So what we're saying is probably here. No.
Yes. Yes, sir. Yes, sir. That oscillation here.
Now what we're saying here is, so let's say you have a system, right? A simple system of atom. Okay. We are representing by a 2-level system like this. Agreed?
Yeah. Yes, sir.
Now, when it interacts with a cavity, it exchanges energy with the cavity and also comes back. There is this interaction back and forth of energy between the atom and the cavity, right? So that combined system is basically called as a dressed atom. Okay. Now, because of the cavity resonance, the individual level becomes 2 levels in upper and lower states. Okay. Okay.
Yes, sir.
So now, because of which, if you look at the fluorescence of it, okay, you look at basically absorption followed by, let's take a simple atom and sweep the wavelength. Okay. What will happen? If I sweep the wavelength, let me just copy this to something else. 1 second. I'll copy this, but I don't disturb the main. Okay. Yeah. So now let's take a gas system consisting of lots of atoms like this.
Okay.
And you shine a laser, lambda. Okay. And you scan this. What will happen to the absorption as a function of lambda?
Yes, sir.
what will happen? When this is only atoms, okay, there's no cavity at all. If I have
Okay.
such a scenario, as I shine my light, if the wavelength does not match the resonant wavelength here, correct? If
Yes,
the
sir.
wavelength does not match, it will simply pass through. There's no absorption at all, correct?
Okay.
But if I have a wavelength which matches this resonant wavelength, then you basically have a resonance absorption. So you'll get an absorption peak like this. All right.
Yes. Yes.
Now, this is for absorption. You can also
Okay.
think of a similar thing for fluorescence. Or rather, what we can do is, I'll shine light at much higher energy. Okay, somehow I pump it with a blue light. Okay, so if the wavelength is, let's say, omega naught here, so the frequency of transition is omega naught, I'll pump it with, let's say, omega naught plus 1 eV. Much higher energy photon I'm pumping. Okay. So now when I do, let's assume that there is some kind of a state which can accept it also. But anyway, so now when you have these excited atoms, in an atom case it becomes slightly tricky, but you will have fluorescence if you look at the fluorescence now, let me just now plot as a function of lambda, what is my fluorescence? FL, fluorescence.
Yes.
What will be my fluorescence signal? If you have a simple atom, what will be my fluorescence? Or rather, let's not even, somehow we excited the atom. Let's not even worry about it, okay? We have created, we have excited the atoms to higher level, higher energy state. It can be electrical, it can be optical, something we did, and we have excited these atoms. Now, if I look at fluorescence as function of lambda, if you have an atom, what will happen? Yeah.
So we'll get two or more peaks. We'll get.
No. If you have a simple atom without any other signal, you'll get a single peak.
Okay.
Only one atom, no? Only this transition. Basically, atoms will go from this excited state to the ground state. You'll only get one atom, one fluorescence signal. Okay?
Yeah.
Now, if I somehow make the cavity, how do I know that the cavity, this is energy levels of my dressed atom? How do I even know this? By looking at the spectroscopy. Okay. Now, if you have these atoms placed in a cavity like this, let's assume you're placing it in a cavity, a mirror like this. Okay. Now, this cavity has a resonance frequency, which is slightly different from the fluorescence of this. Okay. Now, they will interact and cause these two levels to form, which are called as dress states. Okay. There's a Rabi oscillation frequency here. There's a Rabi oscillation frequency. Basically, the spacing is this Rabi oscillation frequency. And you have these two levels which are created, sublevels. This is because of the interaction of the atom and the cavity. Okay. Or rather, in some sense, atom and the photons that are present in the cavity. Okay. So now, what happens is, if you do fluorescence on this system, same measurement. Now, instead of getting one peak, you end up getting 3 peaks. Why do we get 3 peaks? You can have a decay from this excited state to this ground state. That is omega naught. Okay. You can have excited state to this state, which is omega naught plus omega Rabi. And this is minus. Okay. And there are 2 of these transitions which are going at omega naught, right? So you have 3 different frequencies or wavelengths which are emitted. And that is what we are seeing here as an experimental. Theoretically, we expect this. And if you try to measure this as a function of this detuning, essentially means that we are shifting we are scanning the frequency of the laser or the wavelength of a laser across the resonance, and they're slightly away. I mean, this frequency shift is 100 megahertz. It's a very, very small amount. For example, if you're talking of, let's say, 780 nanometers, as a, let me take an example of, if you take a 780, this omega naught, let's say, corresponds to 780 nanometers. Okay. Now, a frequency 780 nanometers will correspond to How much of frequency? Can somebody tell me that? This will be C by 780 into 10 power
780 into 10
minus 9, right?
Yeah.
So it will be something like, let's assume, okay, let's make it, so let's simplify our life. And let's call this, instead of 780 nanometers, okay, yeah, somebody calculate and tell me, why to simply make these guesses. 3 into 10 power 8 divided by 780 into 10 power 9 minus 9 becomes how much? Someone? Some terahertz. Correct?
3.84, 10 power 14. Yes, sir. 384 terahertz.
384 terahertz. Thank you so much. 384 terahertz is a frequency. Now, this frequency shift of 100 megahertz corresponds to delta frequency by mu naught. Let's write it in the same language. Delta omega naught divided by omega naught equal to delta lambda divided by lambda. This is the relation that holds true for the how much change in the frequency. So, since we are talking about frequency shift of 100 nanometers, 100 megahertz, delta lambda will correspond to how much? This is 100 megahertz, 100 into 10 power 6 divided by, let's make it 400 into 10 power 12 into 780. 10 power 780 nanometers, only we'll leave it, okay? Can somebody tell me how much this is? One-fourth. So this is 0.25 into 10 power minus 6, right? Into 780. So this is effectively like a femtometer. Very, very small shift in the wavelength. It is not a very large wavelength. Okay? We call it detuning of this wavelength. Does it make sense? Okay? 100 femtometers or something like that, 0.1 picometers kind of a wavelength. So you need extremely sharp laser lines. We tune it slightly, and then we get 800, so this is 200 femtometers, something roughly like that. Okay? That's why we call it detuning, and because we are not comfortable dealing with femtometers, we are talking about megahertz. Anyway, all right? Chinal, anything else that we can add into this?
No, sir. I think this is apt. What you said.
Does that make sense, Swapnil?
Yes, sir.
Yeah. So we can even, actually, next time we should make some questions in this direction. Please, somebody note down.
Yes, sir.
We can make a nice question around this next time.
Yes, sir.
Yeah. Any other questions, guys? I don't think we got any questions on the Excel sheet. Nandana, do we have any questions on the Excel sheet?
No, sir.
Oh, no. Okay. Raj Kumar Thakur?
Hello.
Hello.
Sir. Hello, sir.
Hello. Nice to meet you, Raj Kumar. Can you introduce yourself?
Yes, sir. So myself, Rajkumar Thakur. I am pursuing my Master of Science in Physics from Sri Sathya Sai Institute of Higher Learning. I hope.
Oh, I see. I see.
Yeah.
My alma mater.
Yeah.
So say hello to Gauri sir and everybody
sure.
else.
Yeah, sure.
Yeah.
Sir.
Yeah. Okay. Yeah.
Sir.
Yeah. Tell me.
I was having one doubt, like while preparing for final exam, like for the case of Nano Photonics, so which book should we prefer, or just by?
Don't worry about the books. Just look at the lecture notes and assign.
Yeah,
that's all you can do.
Yeah.
I mean, these things don't have. I mean, I have always. For example, quantum optics is very easy. Just look at this. This 4 weeks will be essentially from this book. Okay, this is almost like a one-shot reference for quantum optics. But I mean, so the Lorentz oscillator and all, the Mark Fox's book, what is that called? Optical Properties of Solids is pretty good.
Yes.
But in between metamaterials and all that, they are from many, many different sources. Yeah. Okay. Yeah. Any questions about this?
Sir, like I was having one doubt.
Yeah.
that this split ring
Okay,
resonator, like, so can you explain it once more? Like,
let me look up. Yes. Is this split ring resonator?
Sir, week 6.
Week 6. Okay, fine. Yeah. Now the question is, see, nanophotonics is all about trying to control the... Jinal, you want to take a crack at it? I can move the slides.
Yeah. Okay, sir.
Yeah. He doesn't understand split ring resonators, so please go.
Yeah. Hi, Rajkumar. Actually, this structure was introduced to incorporate like negative permittivity, using plasmonic materials. So basically, like if you recall, to get a negative permittivity, we need permittivity and permeability both going negative. Then only we can have a negative index material. So now the thing is like plasmonic materials, like as such, they don't support magnetic resonances. Like, but dielectric on the other hand can support magnetic resonances. So the split ring structure, like here also, like if you can see here, this metal dielectric composite. No, sir, sorry, sir. Next slide on.
No, okay. Yeah. You want me to stay here?
Yes, sir.
Okay.
Yeah, so basic necessity for magnetic responses, we need to have a circulating electric field. And as you know, like metals can't have any electric field inside because of high charge density. Electric field is only at the surface. It's been screened out by high electron density. So in order to have a circulating electric field, or in other words, to have a magnetic response, we need to engineer a structure such that we can have a circulating field. So like sir has explained here different, like if you have just a disk, there is no way in a metal we can have electric field. So this circular disk or sphere or anything can never have a magnetic response. Similarly with ring structure, because of symmetry and all that, still the induced currents will flow in the opposite direction and still there will be no magnetic response. So this is split ring which has been introduced, and like there are multiple ways to explain in terms of capacitive and inductive response and that. So here response. Yeah, here like by seeing the gap, like depending on the gap, we can have a circulating electron, because like let's say like in the C shape, like one of the end might support another charge, and on the opposite side we have the like negative image charge, the image charge of that, and because of which like there can be a circulating electric field. So this is how magnetic response is being engineered here. So like you can add it, I think.
Okay. Yeah.
Yes.
So Rajkumar,
yes, sir.
I think Jinal has broadly covered. Just to phrase it again, what she said, I'm just repeating in some sense. Okay. If you take a pure metal, okay, just take a metal sheet. What will it be? What will be its magnetic? What will be its mu and what will be its epsilon? Any guesses? Yeah. So my question is, let me repeat. I have a sheet of metal, bulk sheet, okay? A sheet of metal. Okay. What will be its epsilon and what will be its mu? That's the question, right? Finally, because, as we discussed many times in the course, nanophotonics is all about engineering epsilons and mu's. Okay. We cannot change much about the frequency. The light, it always travels. Wherever it is, the Maxwell's equations are same. Okay. Maxwell, I can write the same Maxwell's equation for myself and for you. It's still the same. Only thing that will matter is the distribution of epsilons and mu's in between different bodies. Okay. So that's the problem. So now if I take a sheet of metal, what is the epsilon and mu? Okay, Rajkumar?
Yes.
So we discussed in the first or second week maybe, we said metals can be described by what we call as a Drude model. Okay.
Yes.
Drude model explains the epsilon of metal. Like epsilon equal to what? There'll be something like this, 1 minus. Now let me try to recollect. I don't remember these formulas very easily, but I can always write it out. Okay. Is this correct? There should be. Huh?
Omega p square by
omega. Good. Omega p square divided by
omega.
Oh, that's enough, no? Yeah, this is a metal, no? So we don't need anything else. Yeah, that's a Lorentz oscillator, omega square, right? As frequency increases, what happens to the permittivity? As frequency is, if the frequency is very low, what happens? Okay, so in this case, if you plot as a function of frequency, the behavior will be something like this. Okay, so you have permittivity of epsilon equal to 1. At lower frequencies, you have a large negative epsilon. Right? This is the solution. Right? Now the question is this enough? This has been studied for 30, 40 years, since 1970s easily, right? Is this enough to achieve negative index? Okay, that was a context. That was the main problem that people are still waiting to get a Nobel Prize for. Okay. Can we have a negative index material? Okay. Is negative index possible? So if you look at the analysis that we did towards the end of first week and also in the third week, I think we need two parts to it. Okay. And basically goes as epsilon and mu. This plus or minus will be there. And we have argued by several ways that you need to have simultaneously, okay, epsilon and mu negative. I mean, not very strictly, but yeah. Okay. If you have a purely non-magnetic material, you cannot have negative index. Okay. We argued that with these diagrams, right, wherein we have drawn this real and imaginary axis, and we have argued that. You go back and look at the first week, you will see that you cannot have if you have a purely non-magnetic material, you cannot work with that. Okay. You need some kind of a structure. So now the question is, will this sheet of metal have will have any magnetic property? Let's assume that it's aluminum or something. Okay, it's not a magnetic material. Let's assume that it's aluminum or gold or something. Okay, its epsilon basically is going to be epsilon naught. Sorry, not epsilon, mu. Mu equal to mu naught. Okay, so with this you cannot have any magnetic response. Now, how do we engineer a magnetic response? What do we know from our Lenz's law? If you take a sheet of metal and I keep having circulating current like this, okay, it behaves like a current loop, right? Amperian loop. And it has a magnetic B response, right? B field. What's the direction of magnetic field now? Rajkumar?
Yeah, it will be opposite to the
opposite, or basically whenever there is current loop,
yeah,
the right hand thumb rule, right?
Yeah,
right hand, right? B field is pointing out. Pointing outwards. Okay. Now, if you have this, yeah, this suffices. But the problem is, this is definitely here, mu is not equal to mu naught, but it is very, very weak, what we call as diamagnetic. It's not really strongly magnetic. Okay. That's what I said here in this. If you look at this, what is that? Week 3, right? Week 6. We said that this is only weakly diamagnetic response. Mu is slightly less than 1, but it's not enough. Okay. Okay.
Yes.
And now, other thing is also that you have, where is this? If you're having a current loop like this, the center of it is not really doing anything. Okay. The current is only flowing at the edges of the ring. Okay. So if you look at the response of a sheet like this and compare it to the response of a ring like this, both will have mu less than 1. Okay, both will have the same magnetic response, but it is not strong enough. Okay, not strongly magnetic. Okay, now how do we make it strongly magnetic? Here I am actually making a leap, which you probably will not know. There is nothing you can do about it. Okay, so if you look at L, we typically associate that the inductor will typically associate with magnetic response, capacitance with the electric response. Okay. Now we know that if you have a L and C combination, we have a resonant frequency which is 1 over root LC. Okay. Now the challenge is I have to create a resonant LC circuit. This has no capacitance. It has only a mu L inductance. The current flow, basically the resistance to current flow is the inductance. Right? You have a current loop and that is the inductance. You have to also create a capacitance. How do we create a capacitance? We say, okay, let's take this and let's create a loop and a cut in this. Okay. This is my structure which has a capacitance here, right? Plus and minus separated by air. Right? This is a capacitive structure. And there's also an inductive response coming because of this. So this kind of a structure will have a resonant frequency, which is roughly of L and C. Okay. Now, if you make your ring gap smaller, okay, if you take this gap and gap smaller, what happens? Rajkumar?
Yeah.
What happens if I reduce the gap? Think of a parallel plate capacitor, plus and minus Q. The gap, right? Capacitance is epsilon by D per unit area. If D reduces, capacitance increases. So the resonant frequency should reduce, correct? By controlling the gap, you can control your resonant frequency. And whenever you have a resonant frequency, you have a very strongly dispersive element. And you can have, at some point, both epsilon and mu to be negative. And that is what I think I have shown in week 1 somewhere. Let me look up this. Was it week 1 or? I'm sorry, I think I forgot it. Maybe week 3. Yeah. Yeah, right? In this case, I'm able to get a dispersive structure like this, and I'll get both epsilon and mu to be negative at certain frequency. And with that, we can create a negative index material. All right? Does that explain the idea of a split ring resonator?
Yes, yes.
So you see here, this is what I was referring to. Regular dielectric, you'll have mu to be 0, 1, no imaginary part. Real part will be something like this. A combination of it will have something like this. So even if you have a pure metal but non-magnetic, mu will be here and epsilon will be here. So n is only 1. It doesn't have any negative epsilon. N is only exactly 0. Sorry, it's not negative. If you want negative, you need to have a magnetic response. Okay. Rajkumar, by the way, are you in first year or second year MSc Physics?
Second year, sir.
Second year.
Yeah.
Okay. Yeah. Okay. Do reach out. If you have any questions, please reach out to me.
Yeah, sure.
Yeah. Any questions? Anything else? Ayushi, I think she came and left. Lakshmi, any questions? Okay. Gina, anything to be added?
No, sir.
Okay. Guys, one thing, we are always looking out for interested students who want to do their projects or, PhDs and so on. So, yeah, if any of this kind of interests you, feel free to reach out. Okay. Especially, if you have things like JRFs and all, or even our PhD program right now, we made it open to even, it's more physics than electrical engineering, or rather we work at the intersection of physics, electrical engineering, materials, and so on. So we are happy to have very motivated students who are interested in PhDs or projects and things like that. So it's an open call. You can reach out.
Sir,
My TAs are all on the call, or you'll find them on the website. Okay, it's not been updated for a while, but I'll soon update the web page also. So reach out to them on LinkedIn and things like that. Ask questions. It's always fine. Yeah. Sorry, somebody was asking a question.
sir, I wanted to your main field is in photonics, but you are having some more my interest is in biophotonics. So I wanted to do some project really about research on it by biophotonics. So is there can you advise me where should I approach?
No, actually, I don't know much about biophotonics. I understand the scattering problem and all. I understand at a high level, but I don't work on it, so I don't know who are the people who are doing good work in that direction. Unfortunately, I don't know very much about it. Yeah. But I mean, the best thing to do would be what are the most interesting challenges in biophotonics? Who are the people who are those interesting challenges? And you try to go into that. Okay. To me, one of the interesting things of biophotonics is like optogenetics. And,
I was
but I don't know of anybody who works in these things. So I don't know personally. I mean, there are scientists, of course, I know about it. So the question is, can we control the neural firing and things like that with optical signals? Can we control can we detect the neural anomalies or issues with the brain with magnetic sensors? There's a lot of interesting things that are being done. Unfortunately, I don't know enough about it. I have stayed away from bio because they feel that it's too complicated. I'm sorry, Rajkumar, I don't have a better answer than that, but that's the honest answer I know.
Yeah. Thank you, sir.
Guys, anything else? Well, see, one thing I'll share with you. See, these areas, these are fairly advanced, and it's not. You cannot understand these things by listening to lectures. Okay. You will understand only by asking questions. Okay. So it all will make sense. I mean, when I talk about it, it all feels like, yeah, it's all good, I understood. But when you have to explain it, I think you'll start feeling that, okay, there are some gaps in my understanding. Okay. So my suggestion would be not to follow everything that I say in the lectures. Try to, without listening to my, audio, you try to look at the slides and think what I'm trying to say in that. Okay. Once you have some kind of an idea about the topic, then you can come back and listen to it one more time or something like that. It doesn't happen in once, because honestly speaking, I think when I look at the course content, it can be pretty involved. So you should look at it twice, thrice. If you look at it the first time, I think you'll not be able to grasp a lot of it. Okay. It's basically 10 years of my effort, 10, 12 years of understanding of things and all that. And a lot of it is from my PhD students, including Gina here and my previous PhD student, not now. So a lot of it is because of all of their help and all that. We'll get it. Okay. So yeah. All right. So please do ask questions. We're happy to answer any of your questions. Okay. Yeah. Yeah. Tell me. Come on. Yeah.
Sir, actually, I have a questions, but that's not related to a course.
Okay.
So actually, as I said, all the meta surfaces and this can be think of an LC circuit.
Think of as a
Hello. LC circuits, LC
okay.
resonant circuits.
Okay.
So when I come across some literatures, I saw they have created an equivalent circuit for their entire structure.
Right.
Can you suggest me some things that I can explore about this equivalent circuit model? How can I understand this? How they have interpreted how they created such equivalent circuit to the structures? So, is there any source to understand and explore?
I cannot tell you one particular source, but I think a lot of this equivalent circuit idea was pushed by Nether Engeta and Andrea Alu. This is from, you look at their groups in basically in the time frame of 2006 to 2010-ish, right? They have pushed a lot of these ideas. Okay, this is one group. There is also a group, I mean, you have to check, there will be some papers by them, and I don't know if they have written a book or not, but there is definitely a book by Kostas Tsoukalis. This is called, I think, wave propagation in something. Okay, propagation in some media or something like that. This could be one reference. I'm not sure if exactly they have touched upon LNC and all this. There will be another book by this gentleman from Finland. I forgot their name. Jinal, do you remember? This Finland, Russian guy in Finland.
Sir. Alex Krasnov? No.
No. Krasnovsky is now in Florida, right? UCF.
Florida. Yeah, Florida.
No, this is
yes.
Trachekov. No, not Trachekov. Who worked with Arseny?
Yes, sir. Worked with Arseny.
Not as, yeah, I mean, Russian guy. I mean, the original magnetic resonances guy, right?
Oh, okay, sir.
Evlukin,
sir. Andrei Evlukin.
No, Evlukin or...
but he's more
also,
with electric electronics.
No, yeah. Evlukin is more of a me theory, right? There's a guy,
Yes.
Finland. I forgot his name. Maybe Trachekov. Okay.
Yes, sir. Like he works mostly with the RF metamaterials. So yeah, he has circuit
interpretation, right? Yeah.
Yes, sir.
Interpretation. He has a book also, I think, or some kind of lecture notes. Okay.
Okay, sure.
Sergey. Okay. This probably will be a right reference. Alu's papers are there, but papers may not give you everything. But this will be more mathematical. You find the right balance. Okay.
Yes, sir. Yes, thank you.
Yeah. 1 and 3 probably will be the right choices. Okay. Yeah. Anything else, guys? Okay. Gina already found something.
Yeah, like I sent a link. This is like just basically plasmonic particle on a mirror, like circuit model of that.
I see.
Because our course discusses more on the plasmonic resonances. So.
I see. Okay. This is interesting. Why should this have a magnetic response? No, it won't have, right? Electric resonance?
Yes, sir, it has the gap plasmon. It will have the magnetic dipole resonance.
Yeah, okay. From the gap mode kind of, you'll have. Okay. Good. All right. Okay. Anything else? Okay. Yeah.
So there was one assignment problem, I think, from week 5. Yeah, that's my question. Yeah, question was like periodic diffraction criteria is fabricated in a glass with the refractive index 1.5.
Sorry, Rajkumar, there is a little bit of background.
Oh.
Can you repeat?
Yes, sir. Question is periodic diffraction grating is fabricated on a glass glass substrate with 100 slits with a periodicity of 2 micron. And the EM wave is incident normally on the grating, resulting in a second order maxima. So tending at an angle of plus minus 30 degree with respect to normal. So what is the wavelength of the incident wave? So like I tried this, but yeah, it was incorrect. So can you, which
I don't know.
question
I mean,
was-
we are talking of
question
2D
was-
sine theta equal to
Yeah, yes, sir.
m lambda. You are saying m equal to 2.
Yeah.
And periodicity is how much?
Periodicity is 2 micrometer.
2 micrometer. Sine theta is 30 degrees, right? So, sorry, this should be, yeah, this should be it. Normal incidence, so this should be it. So, this will be half. Right?
Yes, sir.
I don't know. Lambda equal to 1 micron.
Lambda is
No, the only issue is the substrate refractive index you have to take. Correct?
the refractive index is here given 1.5.
I have not taken substrate refractive index here. Jinal, over to you.
Yes, sir. Like, yeah, I'm just like finding that question.
So it should be what? I mean, okay, let's solve it. Right? This is my grating. What is the K grating? 2 pi by 1 micron.
And now, so it's fine. Like, so now 1 micron and then the index is 1.5.
That's what I'm thinking. Yeah, you have incidence from the air or from the glass?
An incident from
So from the air, incidence is from the air, and the transmission is there. So resulting signal.
2 pi by lambda naught, right? And K grating or K glass will be 1.5 into 2 pi by lambda naught. This is parallel, right? They should sine theta component as well here, right? This is my angle, right? So this should be sine theta, correct? So they should be 1.5 2 pi by lambda naught sine theta plus K grating, which is 2 pi by 1 micrometer, should be equal to 2 pi by lambda naught. Is this the problem?
Yes.
I don't know what you get. You please solve it. Okay. And you can just paste, take a picture and send it to us. We'll verify it. Is that okay? All right. Yeah. Anything else? Okay. If not, I think we can stop here. Yeah. Everyone, we can stop, or you want to ask something else? Yeah, please let me know if you have any questions. You know, we can always answer them. Okay, please reach out. I don't think this forum has been very active, no, Gina?
No, sir, not yet. Like
First couple of weeks,
first
there was
one.
question. Yeah.
Yes, sir.
Okay. Yeah. Maybe we do one more round of this and we stop, I think. Let's see. Okay. All right, guys. If not, we'll stop here. Thank you very much, everyone, for joining. It's late. I guess it's time for you to have dinner. We'll see you all next time. Let me know. If we don't receive anything, maybe we'll have another session in 2 weeks from now. All right? Yeah. Look forward to meeting all of you. Thank you so much.
Thank you.
Bye. Bye.
Bye.
I think moderator, you can close this. IIT Madras team. All right, I'm signing out.